Hi, I'm Jason, and welcome to this section of the Chemistry Tutor. In this section, we want to talk about the periodic table of the elements. Now, we've been talking about it in several sections up till now. I think I've even had you talk about atomic mass and atomic number and things that are listed on the periodic table. So I've definitely already given you the most important tools to really use that periodic table. But what we want to do in this section is kind of look at it as a whole unit and really try to understand a little bit more about how it's organized. When we get way down deeper into the course later on, we'll go into this in a whole lot more detail even than what we're doing right now. But there's still some really cool things that we can learn just by looking about how it's laid out. So we're going to do that right now. So I encourage you to pull your periodic table out of your textbook. If you have a chemistry textbook, just open it to that. We'll have a graphic overlay here to show you some things, but it's important for you to pull your table out because on your test, that's probably what you're going to be using. So let's go ahead and do that now. We'll look at the periodic table. Notice that every element has a chemical symbol that's in bold letters usually, and it's right in the center. So we've talked about this before. H for hydrogen, O for oxygen, He for helium, things like that. So that's the first thing you need to know, and that's going to come into play later when we talk about chemical compounds, because we'll be using these symbols, like H2O, for instance. We all know that that's water. Okay, after that, most periodic tables, if you look just above that chemical symbol, you will see a number, and that number is the atomic number. That's the number of protons in the nucleus of this atom or this element, and we've talked about that over and over again, that every element on the periodic table has a unique number of protons inside the nucleus, and that determines what element you're looking at. So if you kind of scan across, you notice that hydrogen has an atomic number of 1. That means there's 1 proton in the nucleus. If we scoot over to the right, helium has an atomic number of 2. And so on and so on. We could go down the way. We could see that carbon has an atomic number of 6 and oxygen has an atomic number of 8, for instance. So it's telling you at a glance how many protons you have in the nucleus. Okay, now underneath this chemical symbol is another number that's almost always a decimal. It'll have a decimal point in it. That is the atomic mass. If you have a very old chemistry book, an older chemistry book, you might see it called atomic weight. But it's referencing exactly the same thing, but most newer books call it atomic mass because it is really talking about mass. And so that is the mass in atomic mass units that we've talked about in the previous section. So those three things, the element symbol, the atomic number on top, and the atomic mass on the bottom, those are the most, honestly, the most used and most important things that you'll have on your periodic table, and that is mostly what you're going to use it for during your class. Some periodic tables are more elaborate than others, so your book might have the name spelled out in addition to the symbol. Even fancier tables on the internet or that you could purchase might even have the boiling point, the melting point on there. Lots and lots of information that you can put, and that's great. But for a chemistry class, really the atomic number and the atomic mass and the symbol are really the most important things. Now, if you back out and zoom out on your periodic table and just kind of look at the whole thing, it has kind of a weird looking shape to it. And that's the first thing that strikes everybody when we start studying this stuff, is that you think of a table as a nice rectangular thing, but the periodic table has these jagged edges everywhere and there's holes in it, and it doesn't make a lot of sense. Now, we're not going to get into all of the theory why that's the case, but there is a theory behind it, and we'll get into it later, and it has to do with the way the atoms are constructed. But by and large, if you start on the upper left, you'll see the atomic number of 1, and then if you skip all the way over to helium on the right, you'll see atomic number of 2, and then if you go back to the left in the next row, you'll see atomic number 3, and then go to the right, you'll see atomic number 4, and then number 5, number 6. So the atomic numbers are going left to right in a larger fashion, and then you go down one more row, and then they'll start over and they'll go up and up and up as you go across, and you go down one more row and they'll go over and over across there. So the periodic table is really, by and large, laid out in order of atomic number. That's really the major breakthrough that allowed it to happen and allowed it to be useful, and you'll see why that's kind of cool later on. But basically, as you lay it out, it's increasing atomic numbers, how it's laid out there. Very, very important thing to let you know also is that the periodic table, we call it periodic. Why do we call it periodic? It's because it's basically because when we lay the table out this way, the properties of some of these elements begin to kind of repeat after a while. In other words, the columns here, and I'm not going to get into a lot of detail here, but just so you know, when you lay it out this way, all of the columns here, the elements in these columns have similar properties. Maybe it's a similar color, maybe it's a similar melting point, maybe it's a similar crystal structure, maybe it's a similar, if it's brittle or if it's shiny. But in some way or fashion, all of these vertical columns that we have on the periodic table have similar properties. And that is really one of the reasons why the periodic table is so helpful. When you lay it out this way, you kind of know by kind of scanning down vertically that these elements share some characteristics in common. And we'll get into all of that later when we start talking about the details of the atoms and all that stuff. We'll get into a lot later in the shared properties, but just for a big picture now, know that that is one of the most important reasons why we lay the table out the way that it is because of the shared properties that we see vertically in these columns. Speaking of that, it's very important to let you know the terminology. So when we say vertical columns, I'm using that to kind of introduce you to the subject, but really you don't call it that. You call it a group. So these vertical guys are called the groups. So on the left, if you look at your table, this is group 1. And just to the right of that column would be group 2. Now, in your book, also, if you look closely, you'll see, or your periodic table, depending on how it's laid out, but most tables will show that it goes as follows. Group 1A, Group 2A, Group 3B, Group 4B. The A's and the B's we'll get into later. We'll talk about why that's the case. But if you look at the numbers, Group 1, Group 2, Group 3, Group 4, Group 5, basically all of the groups are numbered as you go across. And then when you get over to the right-hand side again, you get back into Group 3A, Group 4A, Group 5A, 6A, 7A, and 8A. So there's this category of A versus B that we'll talk about in a little bit. But by and large, they're numbered, I guess is what I'm trying to let you know. Group 1, Group 2, and so on. And the A and the B we'll get into a little bit later. So those are called groups. That's the most important thing for you to understand. The vertical columns are called groups, the columns. The horizontal rows, what we typically call a row, those are called periods. So again, they're numbered. So the very top one with hydrogen is period 1. The row right underneath that is period 2. The row right underneath that is period 3, and it cuts all the way across. So period number 1 would include hydrogen on the left and helium on the right. And period number 2 would include all of the elements horizontally. If you could kind of slice it all the way across, it would cover all of those guys. Period 3 would be underneath that, would be the row that would cover all of those. So very, very important. So the terminology is important because you'll almost certainly be asked on a test, but also because in a book, if they're talking about, you know, they might say something like, the group 3 elements share the following properties in common. And so you would have to know, what do they mean by group 3? What does that mean? Well, group just means column. 3 means third column. Okay, so we talked about the fact that elements in the same group columns have similar properties. We'll learn about that a little bit later. Turn your attention over to the right-hand side of the periodic table. The very last group on the right-hand side, the very last column, is the elements in the 8A group. Those on the very right-hand side are very special. Those are called noble gases. The reason they're called noble is because they're very stable. And I guess noble, you think of nobility being very, having a lot of solitude and not very, I don't know, maybe not very pleasant to hang around with. Basically, these gases are not very pleasant to react with. They don't react, or they very, very seldom react. So these elements in the right-hand column, such as helium, neon, you might see neon in a neon sign, argon, krypton, xenon, radon. These guys on the right-hand side, they are called the noble gases. So if you see in your book something referred to as a noble gas, don't worry about it. It's just basically they're just telling you and reminding you that it's one of those gases in the right-hand column. I want you to file it away in your brain that none of these gases really react because there's something very important about that I'll get to later. I don't want to tell you right now because it'll just confuse things. But when we talk about producing chemical compounds, that comes into play. These guys on the right, they just don't really do much. You can't really get them to react with much of anything. Okay, now notice in your periodic table that there's a squiggly zigzag line on the right-hand side. So the periodic table, when you lay it out this way, it turns out that you can kind of classify the table in two broad, really three broad categories, right? On the left of this zigzag line, off to the left, most of these guys in the center of the table and off to the left there, they're what we call metals. And that's just kind of like what you would think of. This is where you're going to find your copper, you'll find your zinc, you'll find your aluminum, things like that. Those are the elements that are malleable, which means you can bend them. They're ductile, which means you can draw them into a wire. Most of them conduct electricity. Most of them conduct heat very well. They have a luster to them, which means they're kind of shiny. Those are the things on the left-hand side. Now, the big exception to this, the one that you just have to put a giant asterisk around, is hydrogen on the upper left-hand side. Hydrogen's obviously not a metal. But the reason it's placed there is way beyond the scope of this section. There's a theory to why it goes there. Hydrogen is very special and it does go there, but it is not a metal. So with the exception of hydrogen, these other guys on the left are in general going to be shiny, luster, conduct electricity in general. And we call them metals. All right, so if you hear something in your book referred to as a metal, it doesn't necessarily mean copper in specific. It just means anything on the left-hand side of the periodic table, as we generally call a metal. Now, on the right-hand side of this zigzag line, you might guess if the left-hand side is metal, then the right-hand side is non-metal. And that's exactly right. Look at the elements on the right-hand side of this zigzag. Things like oxygen, nitrogen, helium. Those are all gases. They're all the noble gases on the right-hand column. Xenon, krypton, argon, those are all gases, so they're obviously not metals. So on the right-hand side of the zigzag, you might find gases like that. You might also find solids that are definitely non-metallic, like carbon. Carbon is like charcoal. Think of your barbecue pit. That's carbon. Sulfur, it's a yellow powder. Think of the tip of a matchstick as basically sulfur. Those are all brittle powders. They don't conduct electricity. They're not good to draw into a wire. You can't really bend them. They just break if you try to do anything with them. So you're either going to find brittle solids or gases on the right-hand side of that line. So we call them nonmetals. So the most important thing to pull out of this is on the left-hand side of that zigzag, you've got your metals, and on the right-hand side of that zigzag, you've got your nonmetals. The big exception is obviously the hydrogen. It's on the left, but it's a nonmetal. Okay? Now, that's generally true when you get far away from that zigzag line, metals versus nonmetals. But right around the zigzag line, there's some very special elements that we call metalloids, which means they're kind of like in the middle. They're kind of like transitioning from being a metal to a nonmetal, and they basically have properties of metals and nonmetals. So they're kind of like in between those two guys. So they share the properties of metals and nonmetals. The most famous one is silicon. Everybody's heard of silicon, and you must know by now that silicon is a very special element in the periodic table because all of our computers are made out of silicon. This camera that we're using right now has electronics inside that are made out of silicon. Silicon's very special because it has very special properties. The reason it has these special properties is because it's one of these transition elements right in the middle. It has the ability to conduct electricity in cases when you want it to, but it also has the ability to prevent electricity from being conducted whenever you want it to. So you may have heard of the term, we're kind of getting out of the realm of chemistry, but I'll just tell you, you might have heard of the term semiconductor, like the semiconductor industry, or a semiconductor chip, or an integrated circuit chip. Semiconductor. That's what semiconductor means. You can get it to conduct electricity quite well if you build the circuit a certain way. You can also change the properties very slightly and get it to not conduct any electricity, which is great for making very high-speed switches inside of a chip, which is how your computer basically operates. So silicon is a transition guy. It's a metalloid, very important. Germanium is also another one. We also make very, very high performance circuits out of germanium also. So those guys there's other examples we could list there, but just think about it this way. The metals are on the left-hand side of the zigzag. Non-metals are on the right-hand side of the zigzag. Just around the zigzag, we have these metalloids that kind of have properties of both, and that's really important. Now, the other thing I want to draw your attention to is that notice the way it's laid out. There's giant gaps in the table.